Okay, welcome everyone, and good morning to all of those listening wherever you are in the world. Today I'm really excited to share some of the lessons which I've learned about running potentially malicious code inside of containers, and what code has been run, what kind of impact that has had, and how you can actually protect your systems so that if anyone does manage to breach or break in, or if you do have untrusted code within your systems, you can run that in a more secure more safe manner than what you could using the defaults available to you. So my name is Ben Hall. I'm the founder of a company called Katacoda, which was acquired by O'Reilly Media towards the end of last year. And the reason I'm so passionate about this is because this is a topic which I deal with every day when I'm running Katacoda. If you haven't come across it before, Katacoda is an interactive learning platform for software developers, and it allows you to learn new technologies such as Docker, Kubernetes, service meshes like Istio, all directly on your browser without having to download or configure anything. And what we do is we give you a live terminal session running real software, running on real infrastructure available to you without you having to sign up, without you having to enter any email addresses or credit cards. You can just get started straight away. And so in this example, you can see that we've got a Docker instance running, can launch a Redis container, and this gives you an unstructured way of learning and experimenting in a safe place. And then down the side, we have step-by-step instructions to help you understand key technologies and uh, key commands and key areas of technology which you can learn to solve particular problems, such as how do you launch a container. Now, as you would imagine, when our users come to this website for the first time and they see a nice terminal window, they start to be a little bit creative and they start to explore and see what happens. Hence why I now have these 3-4 years of running untrusted, potentially malicious code, because everyone tries to do interesting things on top of Katacoda. And it's just not just on Katacoda, we run and power lots of other learning portals. So you may have seen us on kubernetes.io, where we're providing the interactive experience there. We're also powering the OpenShift experience on Red Hat, where you can try and learn at learn.openshift.com and understand how OpenShift and their Kubernetes distribution can help solve problems. And this is what's given us lots of awareness and interest. So when some users come to us for the first time, they'll see who they are. Everyone gets root access, so they can install and experiment all they want. But obviously that gives people some interesting capabilities, such as being able to delete everything, and then they get this nice wall of commands where they'll just see everything trying to be deleted. And I imagine because everyone's on their laptop, a couple of you will be trying to do this right at this moment. But that's fine because Katacoda is designed to do this, and that's what Katacoda is set up to do. And that means it's not that interesting. Like being logged into a Docker container and trying to delete everything. Yes, you've destroyed your Docker container and you can't do much with your session, but there's not much else impact you can have as long as you've gone and kept with the defaults and kept in a secure way, which is what we're going to discuss today. But there are things which are also interesting outside of the scope of just trying to delete everything, which causes us a lot of problems. So people trying to DDoS Google, and obviously they see the ping response times increasing slightly, and they think, yay, Google's slowing down. Obviously, that's not going to happen because of a ping, but we do get lots more interesting kind of spin-offs of people trying to launch interesting attacks. And what do we do in order to defend against that? And that's what we're going to discuss. So the agenda is to give a foundational material into container security and what's there and what's available out of the box. And this is covering things like how do we make sure we don't, if you delete everything inside of a container, that doesn't actually destroy your underlying host, and various other interesting capabilities above and beyond that. And then we'll start looking at some of the various different attack vectors which we've seen on Katacoda and we've seen in the wild. So how people manage to run Bitcoin and cryptocurrency mining and how you can detect and defend against that. And then more advanced attacks. So attacking bugs within the kernel, attacking the network, and how you can mitigate against all of these using containers, Kubernetes, and various other cloud native technologies that we have available to us now. So as I said at the beginning, so when we come in, people will experiment a lot with Katacoda. They'll try different commands, they'll see what the capabilities are, and they'll try to delete everything. It's pretty normal behavior. And so what are we using under the covers to make sure that this is something which we can allow and something which we can support without us having to firefight all of the time, hopefully. So there's two key aspects within this, especially around not deleting everything and how deletion manages under the covers inside of Docker. So the first concept is user namespaces. Now, as you saw at the beginning, I said people log in and they're running as root. Now, they can be root inside of that container. And root, obviously, in Linux has a very special meaning. It has lots of privileges, it has lots of unrestricted access. And so when you're root inside of a container, you can install packages, you can override certain files, such as certain process files in the bin directory. You can change modifications on files to make them executable or read-write permissions, etc. You have lots of this scope within the boundaries of the container. Now, if you're running this on your local machine and you run a container, and then you start to mount in certain parts of your file system, such as the directory, your local bin directory on the host, into the container, then because I'm root within the side of the container, and because I have now access to that host directory because you've mounted it in, I will also be able to make all of the changes to that host directory because I'm root within a container, which by default means I'm root on the host too. And so you'll kind of have the same level of permissions. With Docker, this isn't normally a problem because as long as you don't mount anything sensitive, it's not going to cause too many issues. But if you start to mount sensitive files, that becomes a problem. So Docker solved this by introducing user namespaces. Now, the concept of user namespaces is that you can separate the user of what they are inside of a container to what they actually are on the host itself. So inside of a container, you can be running as root, but because that's in its own separate namespace, its own contained kind of area of the Linux kernel, it's not going to have the same level of capabilities as it would if you are root on the file on the host. So even if you are mounting in special directories, special permissions into that container, the root user inside of container is not going to be able to change or modify those. And so you can have this extra level of capabilities and extra level of security. But by default, most of the time, as long as you're not mounting things in, it's not going to be too much of an issue. The other thing which allows us to do is when you start deleting everything and when you start making changes to the file system. Now, under the covers, Docker, everything's run as a image. So when you want to run Redis, for example, or Nginx, you will do Docker run Redis. This will download the container files and all of the layers, and then it will launch that container and you'll have this isolated process running on your system. And if you start making changes to it, it will, under the covers, Docker just adds an additional layer on top. So it's not really recording any changes to the underlying files. All it's doing is changing the modifications to the files on top of that. So the underlying files aren't touched, they aren't modified in any way. So when you delete everything, you're creating additional references on top, which indicate that that file no longer exists. So under the covers, that file is still happy and secure. And so that's why when we delete everything inside of a container, the underlying image is not affected. It's just the aspect of how it looks from a user's point of view. And then as we continue going deeper, there's other capabilities that Docker offers out the box, which is limiting how much access a user has and how much control they have from when they're in a container and when they're in a Katacoda session. So the first is Cgroups. Cgroups limit what resources and what commands and what resources and kind of internal system calls you are able to access, what resources. So Cgroups allow you to limit, for example, what other processes you can see on a system. So if I'm in a container and I list all of the processes, I'm only going to see the processes which I run directly. I'm not going to see other containers. I'm not going to see other processes on my host. And that's part of the Cgroup capabilities. And there's many of these Cgroups, which I'm not going to list here because it's quite involved. But this is one way that you can limit the scope of what a user sees from when they're inside of a container and limit how much capabilities they have access to. Another thing is namespaces. So again, limiting what the user has access to and kind of creating these walls, these boundaries between everything. And then finally, Seccomp, which is limiting the system calls. So we can't change things like the system time, or we can't mount files, or we can't inject Linux kernel modules. Now, all of these are the defaults within Docker, and these are giving us the kind of out-the-box capabilities for free. And above and beyond that, there's some additional ones which don't get talked about too much, but are still giving us levels of protection. And I just want to make sure that we have these covered so that when we get onto the more interesting aspects, we can build upon these foundations. The one which isn't enabled by default, but something which we set within Katacoda, is the no new privileges flag. So this kind of limits that if a user is running as a low privileged user, then they can't use certain flags or certain capabilities to gain root access again. And we just block that out of the box, and that's a flag which you can set when you start running containers. Now, the reason this isn't set by default is because Docker don't want to accidentally introduce breaking changes when you're trying to run your applications, which are built around a set UID and set group ID capabilities. So they don't enable it by default, but it's something which you can set as a flag. And for most applications, you're never going to hit that change. And as long as you have a good testing environment, then you can introduce it and you'll add another layer of security defenses, especially when you're using this combined with user namespaces and low privileged users. The other two undercovers are app armor profiles. So this builds on the top of the capabilities which we discussed here of Cgroups and limiting the resources with namespaces and Seccomp. But these allow you to build a profile of what your application is meant to be doing in this perfectly designed, perfectly crafted world, and and so that limits the profile of what a normal running application should be and what it should have access to. And so if a hacker managed to break in and they start to go outside of those boundaries, their app armor profile will limit them and it will restrict them because it's beyond the scope of what's considered normal. And you'll find there's lots of profiles available on the internet which have been designed around certain technologies. For example, what does a normal MySQL instance require? What does that require when it's running in a secure, um, maintained fashion? And so if it goes outside the boundaries of that, it means that it's something malicious or something unexpected is happening, and we probably want to restrict that because it's not within the boundaries of what we'd expect MySQL to be doing, such as doing port scans or writing to certain sensitive directories. And so this app armor profile will just restrict that out of the box, which means that if that process does get exploited, then we have another layer of defense. And similarly with capabilities, it allows the Linux kernel to group functionality based on the set of functionality which we want to enable or disable. It will limit all of the underlying capabilities that it needs. So for example, we can disable setting the host name of a system. And so instead of having to individually identify what all of the functionality would be to disable setting a host name, we can just disable that as a capability. And there's other capabilities that we have, such as opening network files or raw network sockets, changing the system time, etc. And we can disable or enable that on a very granular level to give us only the security that we require. And this is kind of the aim and what we have with Docker is we want to have an out-the-box secure system, which we can then go in and tweak and modify to make it very targeted and very explicit to what our security profile looks like. And that's because everyone's is slightly different. With Katacoda, we obviously have a much higher risk model than more normal systems because we are giving people access into our system directly and they don't have to jump through a firewall or open a reverse shell or anything like that. We've just given those access to them directly. But obviously, if you're an interesting organization such as finance or government, then your risk profile will be also interesting, increasingly more complex, because you'll have certain people wanting to explicitly break into your system and see what they can find. And so there's lots of categories where you'll see different risk profiles and different setups. If you look at certain online services that you probably use on a day-to-day basis, these have very similar capabilities to what Katacoda offers, and obviously a very similar risk profile. So if you open a cloud shell in Azure or GCP, obviously you have the ability to run any software within inside of their boundaries. And so if you can poke around and do certain interesting things under the covers to discover more about what's happening inside of the systems which they're running. And likewise, if you're running on Heroku or any platform as a service or any serverless technology, you are giving people the capabilities to run code within your platform, which could potentially have malicious side effects. But that doesn't, it's not just hosted services which are prone to attacks. We saw a couple of years ago Tesla being exploited and having cryptocurrency mining run on their Kubernetes cluster. The attackers managed to find S3 secret keys to access buckets, etc. And this was all because they accidentally left their Kubernetes dashboard open to the public. So even though they don't necessarily have a high risk, high threat model, because of the actions and because of misconfigurations, they did accidentally open themselves up to attackers. And as such, the capabilities that we're talking about are all layers of defense which they need in their systems to either detect and protect against it earlier, or defend against it out of the box, so that if this does ever happen to them in the future or another organization, the risk is somewhat slightly reduced. Now, when we see attackers inside of the system, either on Katacoda or if a system has been exploited, it can be somewhat difficult to identify why. So in this case, this is a Bitcoin mining running on top of our cluster. And you can see certain interesting characteristics. Firstly, there's a huge spike instantly in CPU usage as the Bitcoin process starts to initialize. It's taken over all of the cores, which is always slightly suspicious. And you'll see that the process is actually on HStop has got this nice blue color to indicate that it's got a slightly different weighting, slightly different level of processing under the covers to encourage it to run in the background. And so that's why it's slightly different color, which means that it can run happily there forever if no one has got alerting around it. We do, so we can detect that early on. But the interesting thing about cryptocurrency and what we see on Katacoda is it's very hard to tell the difference between is someone doing something maliciously of cryptocurrency mining, or is someone just running a machine learning process and they're trying to learn and understand TensorFlow. And this is the same if you are managing a cluster internally or if you're running Kubernetes and you see a huge spike in CPU usage. If you're letting people run machine learning capabilities, then that could just be a normal everyday behavior. And they're expected to be running 100% of the CPU to train their model. So there's interesting things that we need to do to be able to defend and kind of like mitigate the potentially malicious users from what we consider normal behavior and people learning TensorFlow. There's also other capabilities that we need to be aware of and how this gets introduced into our system in the first place. So leaving Docker daemons and Docker ports open, similar to what Kubernetes does, is a great way to have someone accidentally be running cryptocurrency mining on your system. And so I actually did this on one of my servers a couple of years ago, and I got a nice helpful email from someone on the internet who said this is accidentally open, and they managed to find my email address because my authorized key file had it in there, which was nice and helpful, but also indicated the risk which you're facing with accidentally having misconfigurations on the internet. But it's not just misconfigurations that we need to be careful of. It's also running software which may be entrusted. So in Katacoda, we know everything is entrusted. That's the very nature of the platform. But if you're working with an internal system and you need to have additional capabilities, or you're trying to build on top of existing technologies, it could be very attractive to look at the Docker Hub or look at existing public container images and start to build and work against those to help solve problems, especially if you're under time pressure or if something's happening in production and you need a quick fix. And this is what happened with this news report, which affected a couple of people. So on the Docker Hub at the time, there was a memtest container image, which was available. And so you would download the container and it would run memtest to make sure that your memory didn't have any errors. So something which is designed to run for a long period of time, something which is designed to run in the background and not be paid too much attention to, and then the results being returned. Now, what they did under the covers was at the same time as them running a memtest, they would also be running the cryptocurrency mining software in the background, justly under the covers. And so something which is designed to run for a very long period of time now is also running cryptocurrency and sending all of the discovered or mined um, hashes back to the creator of this. And so this is why it's very, you need to be very cautious when you're trying to run Docker images to make sure you understand the complete supply chain of where that image came from, how that image got created, and it doesn't have anything potentially malicious happening under the covers. And this is another example of where attackers can easily get into your system and kind of jump through. And this is the image report on Docker Hub itself, which was it bypassed all of the firewalls, and then it was just running the memory test, which was very cool. Another way that this is actually capabilities, which I was confused at when I launched Katacoda, is if I'm just running on one instance on one small machine, how am I ever going to have enough resources and enough capabilities to find and discover a hash? Like, how is that ever going to be worthwhile? And what's the actual motivation from an attacker's point of view in order to do this? Now, when you start digging into this world a little deeper, everything's based around miner pools. So there's this collection of a miner pool where you running something for 10 minutes will actually contribute to the overall effort of the pool. And as such, you will get a slice of anything which is discovered by the pool as a whole. So in this case, you can see there've been 15,000 blocks discovered. And so based on that, all of the people who have contributed some CPU or some resources to that effort will get a cut of the payout according to the amount of resources they contributed. So this is why it's very attractive to run Bitcoin on low capability machines, anything which is open to the internet, any resource they can get access of, no matter the performance or capability, because every little helps and everything will go towards this one pool effort, and then they'll start to get a cut of the payout. And so that's why hackers are always looking for exploits, no matter who you are or what you're running and what resources you have available, because there's always some revenue potentially attached to it. And there's huge amounts of miner pools available, and these are growing on a daily basis. At the last count, the block list, which we had, a shared block list, which we look at, had over 5,000 different miner pools available. So it's not like you can just block one and think you're safe. It's an ongoing, continuous mitigated attack vector, which people are trying to use. And again, this is something which the Tesla attack faced, where they was running an private miner pool, which hadn't been reported. It wasn't the most popular ones. But even their firewalls, if they had restricted it, wouldn't have blocked this attack, which we've got discussed here. So it's not just miner pools, which I found are popular, as in things which people like to run on your system. So if you're trying to defend against what is a Bitcoin miner, what is a valid machine learning capabilities and all of these, you can't just have a one list rules everything capability or approach. So you can't just block certain firewall ports or certain host names or certain processes, because there's lots of other things which are valuable for people running on free and restricted resources, either obtained legitimately or because you left your Docker daemon open to the world. So this is a 3D rendering farm where, again, similar to how a miner pool works, you can run a container on a host anywhere. It will register itself with its render farm, and then it will download some assets, run all of the processing, and then re-upload it back to the internet, which is great from kind of like a concept of distributed rendering, less great when you get exploited, because now you are downloading gigabytes of data off the internet, you're burning through all of the CPU, and then you're re-uploading gigabytes of rendered assets too. So it's actually significantly more consumption than what Bitcoin or cryptocurrency mining would be, but also much more difficult to defend because you can't just watch CPU processes to see what's happening under the covers. And then we also have everyone's favorite BitTorrent, which is still around and still being popular and still has a similar effect where exploited servers will be used as a seed and will be sitting there slowly serving traffic. So these are things which we regularly see happening on the internet in the wild or on Katacoda explicitly. And the reasons for this is things like people leaving ports open or leaving dashboards exposed, and that's how they run these types of capabilities. So how do we solve these, and what can we do to protect against them? So again, in the beginning, we mentioned Cgroups. So just to dive in a little bit more about what these Cgroups capabilities are. So these allow you to limit the resources of the process. So you can limit certain things like network. So if you wanted to make sure that one container or one host couldn't take over all of the networking capabilities and affect other containers or other things running on that rack, then you'd be able to limit the networking bytes per second being received or sent. Same with memory, where you can limit how much memory usage a container can have, and CPU. So this now gets into more of a quality assurances. So limiting resources to make sure that if something does happen and if a container does get exploited, it's not going to have this huge effect on the overall hosts or overall cluster that it's running on. And so while Cgroups are great, it doesn't offer all of the capabilities that you need to have in place. So for example, this is a script which helpfully got donated to Katacoda when someone uploaded it. So I dug in and I found the example and the root Git repository and could reverse engineer how they got it running. And so in this case, the script is explicitly looking for low privileged or under-resourced infrastructure, for like a shared VPS, which doesn't have too many cores, and it's self-throttling itself, so it doesn't spike the CPU too high. And so it's trying to go under the covers of any alerting or any systems that you have in place. So if you're alerting for like 90% CPU usage, if they're running the cryptocurrency always at 75%, it will never trigger that alert, which is pretty smart. And I was pretty impressed when I thought this in terms of just how to have that capability and to have that consideration of how people are alerting on potentially malicious activity happening in their production. And so with this is where things like just limiting the CPU shares or limiting the CPU isn't going to be enough. So we need to think of some other ways that we can start mitigating against malicious actions and malicious activities above and beyond the Cgroup capabilities that Docker has in place. So one of the processes is killing long-running sessions or long-running containers. This kind of goes to the whole pets versus cattle discussion we had with infrastructure and servers, but does it more at a fine-grained container level, where we don't want to keep containers running around too long, because if someone does manage to find an exploit into that container, and they do manage to run something malicious in the background, like Bitcoin mining or port scan, or just slowly ciphering off all of your data up to Pastebin or some other online service, then we want to kill that and have that recycled as quickly as possible, just to make sure that any attack vectors are being closed, we're always being up to date, we're always applying the latest security features, security patches, and security updates to that container itself. And the second is being able to block outbound internet access. So this is a lot more interesting. And so this is where we can actually start to limit the capabilities of, for example, the limits that we discussed in the past or previously, where we have Bitcoin miner pools or we have download services like BitTorrent or the server rendering farm, distributed rendering farm, where we can actually limit them by limiting what services our containers can talk to. Now, one way we can do this is IP tables. Now, IP tables can get a little bit hairy depending on your expertise. Kubernetes is built all around them, and it's amazing what's happening under the covers, but it can take a very concerted effort to understand. But if you start to, they can offer you some great capabilities and some great security measures. So in this case, we're just saying we're dropping all outbound access to port 25. So, for example, people can't use people can't talk to a mail server running on port 25 to send out spam email addresses. And this can be a range of ports or anything else um, which we have in place. So, for example, BitTorrent ports or Bitcoin mining tools. Unfortunately, with Docker, this is somewhat more difficult and challenging to introduce. And this is because of the way that Docker works and the way that they can jump through the chain. So instead, there's some other capabilities that we're starting to see which can actually help provide more control over the network traffic, something which will work with Docker and actually provide you more capabilities than what IP tables do out of the box. And one of these is eBPF. So this is a hook, or this is a kernel kind of program this is a program which you can inject into the kernel and into the pipeline, and it will it will hook into certain activities that the kernel is doing, these probe points. And when certain of these things are being executed, it will call back into this user-generated program, and they will verify whether it can or cannot continue to proceed with that system call. So a lot of these capabilities are being used by tooling such as Sysdig for providing debugging traceabilities about what your application is doing. Things like strace, TCP dump, for example, are all building on these probes and these capabilities to track when a system call is being made, when a new connection is being made, and give you some visibility into what's happening in the covers. But with this filtering, we can also apply that to filter out certain packets or certain commands which we don't ever want running on our system. So it's pretty low level, advanced, but it's some capabilities that we're slowly starting to see more utilized more wildly and more broadly. Cloudflare, for example, are using this to mitigate DDoS attacks at the edge of their network. And so as soon as they start to see it, this BPF program will jump in and it will just kill all the network traffic directly. And so that's how they can handle terabytes per second of traffic in a cost-effective, scalable, maintainable way, because they are at such an early point within the kernel to filter and detect against this. So it's very cool technology, and there's lots of great resources on GitHub if you wanted to investigate more. But if we wanted something a little bit more manageable, a little bit more maintainable and accessible, then IP tables and eBPF are pretty low level, and higher level is network policy and service meshes within Kubernetes and the cloud native ecosystem. So within Istio, which is the implementation of a service mesh, there's others like Linkerd and various other service meshes which are available depending on what your preferences are. But the general capabilities are they have an ingress gateway to track and manage all of the traffic coming into a Kubernetes cluster. In this case, that ingress will forward traffic on to the certain applications running inside of your application. And again, these will forward and talk to each other internally. And then any traffic going outbound will always also pass through this egress gateway if you have configured it to do so. And so this gives you an API hook into all of the interesting networking parts within your system. So now you can block traffic coming in from the ingress gateway. You can rate limit and shift traffic between services to not overwhelm them or to provide additional firewall protection so that certain services within your application can't talk to each other. And then you can also limit what services can be called outbound. So, for example, if you are going through a proper CI/CD pipeline and you have built your container, you have deployed it into production, there's very little reason why that container should ever be modified again. Like it shouldn't have to go out and call the internet to do an apt-get update, or it shouldn't have to download and install additional packages because it's running in production. And we should have a pipeline to manage that, or it should be running and managed as a separate container or something, a debug container attached to it. So we can restrict that by making the container read-only or blocking all of the outbound traffic. We can then just limit only the APIs that we know our applications are talking against in the outside world. So maybe an AWS endpoint, or maybe a GCP authentication service or storage bucket, for example. And we can just give access to those particular things. And so that means that our applications are significantly more secure if, or our data is more secure, because if someone does get, if an application does get exploited, then they're not going to be able to upload data to an external third party. They're not going to be able to connect to a miner pool, or they're not going to be able to pull down additional exploits or additional scripts to run because our egress gateway has blocked all of that outbound traffic. And that's kind of some of the capabilities that we're running and some of the capabilities that we have or that's available to us. It's a constant game of cat and mouse. It's always, new capabilities are always being introduced. New features are always being enabled that we need to be aware of, both from what it can do to secure us, but also what it can do to introduce potential new attack vectors as well. So we always need to be ahead and up to date on what's happening. And the reason this is important is because people can find an exploit in a very small part of the system, and then they can use that to piggyback and use that as a jump into other parts of our internal system, which may not have had quite the same security defenses, and kind of sneak in through other activities without us noticing what's happening. And this is where we can start looking at what's happening at like a host level or a kernel level attacks, and what these are being utilized to mitigate or kind of like find other exploits into a system, even if we are running egress and we've blocked certain access. So the third thing that we used to see more commonly, and we haven't seen too happening or discussed too frequently, but definitely something people need to be aware of, is the concept of privileged containers. Now, privileged containers, when you're running these inside of Docker, remove all of the security capabilities that container has. So all of that goodness, which we talked about at the beginning, such as it blocking Cgroups by default, being able to limit what other processes it can see, being able to limit how much resources or capabilities it has, for example, installing kernel hooks, mounting file systems, setting the system time, etc. All of those goodness gets removed if you set this privilege flag. And so you need to be very aware of why this is being run and potentially just blanket block it in your capabilities because it does introduce, remove all of the security. And if you find, or if an attacker does manage to find a privileged container within the system, it's very easy for them to jump out and attack their host. So in this case, I'm inside of a privileged container. I can look at all of the disks and all of the file systems very easily because we can just ask the kernel to tell us that. In this case, we can see that there's a virtual disk 1 and it's got 20 gig. I can make a quick temp directory and mount that directory, mount that disk into it. Because I'm a privileged container and I'm running as root, I have full access. Once I have access to the disk, I can navigate it as I would if I was running on the host. For example, I could go to the SSH directory and I can look at all of the authorized keys that have been assigned to that host, or I could add my own key. And if that, if port 22 was exposed to the internet, I would be able to access the host directly and then have kind of unrestricted and filtered access because I'd be logging in as a root SSH user, and then I could hide myself through various different means, and it will hopefully go, as an attacker, hopefully I would go undiscovered. So this is why privileged containers should be considered very carefully if you're looking at using them, and ideally just block them across your entire system, which is what we'll talk about how to do that in a moment. Other things which we said are the Seccomp, Seccomp, AppArmor, and capabilities. So to go a bit more deeply into what's happening under the covers, if we run an strace on a process, so this is a change in file modification, and the permissions of a file, we can see all of the system calls being made by that application. And it's surprisingly a lot for something which I would consider quite straightforward, like changing file permissions. It does a lot under the covers. So it's checking to make sure it can access or the executable, checking to making sure it can access certain things, loading in certain libraries, setting certain permissions, and making sure it's in the right place. Then finally at the bottom, it's calling the system call under the covers to change the permission for a file to read only in this case, and then it's closing all of the sockets it's created to the various files. So with seccomp, we can limit what system calls are being made. So at any point in this trace, or whatever any point with in our application execution, we can say whether that should be allowed or disallowed. And so this is what Docker's done under covers to block things which it knows are malicious and going to open up security exploits. And we can extend that list, and we can add our own capabilities depending on what we're trying to achieve. So in this case, we're allowing files to be open and read, or the system called open and read. If the chmod system call ever gets made, then that will error, and it will error saying operation not allowed. And so we can ensure that our container would never have the capabilities to change file modifications. And this is actually, this capability is what fixed a lot of the security issues which Docker had in the very early days, or potential security issues Docker had in the very early days, and build a much more robust system out of the box. And so this was from way back in 2014, and that's why they don't have many today, because they have this seccomp profile handling everything. But what the exploit was basically doing was looping through every single file handle on a system, trying to find an interesting path or an interesting file handle which mapped to an interesting file on the disk. And it was doing this by being able to directly call this open by handle at function. So it could open everything, every single file within the system. Now, by blocking that one single system call, they mitigated this risk and they mitigated this capability and this security attack vector, which is great. Now, there are other things that are happening under the covers which are a bit more difficult to defend against. So with Docker and with container systems, everything is running against the same kernel under the covers. So when I do anything like an uptime or ask for the kernel information, the container itself will talk directly to the shared kernel, which is being accessed by everything else on the host. So I can see what kernel version it is. I can see information like the uptime, which CPUs it's running, other disks on the file system, for example. And this is really interesting when you start to poke around, you start to look at other inline systems. For example, if you're in Cloud Shell, you can say, tell me what CPUs are running under the covers. And this is like nothing too sensitive or interesting from a like nothing too no sensitive information is being disclosed really at this point. We know the CPU model number, but as we had the Spectre attacks recently and the meltdown, we started to flag whether that fix had been whether that patch had been applied to the CPU itself. So now when we do this, after all of our CPU information, which is generally just passing flags, we can now also see if we still have these kind of CPU bugs in patch, and we could potentially run an exploit against those. So this information, which was generally harmless, has now become a source of an attack vector because we can start to identify the CPU, the model, and which bugs have got known aspects to it as a way to potentially breach secure vaults or some other capabilities. In terms of Cgroups, we can look and to make sure and see if they've been applied correctly or what Cgroups are in place. And so in Katacoda, you can say, and if you're inside of a container, you can ask what Cgroups have been applied. And so in this case, you can always check to make sure that you're in Docker, it's got the Docker defaults, and so there's that default restrictions in place. We can also start to poke around, and we know it's Docker when it's on Katacoda. If it's in Azure, it's Kubernetes, but it's the Cgroups, the kubectl First of all, C-group limits. And so now we know that Azure and this Cloud Shell is being backed by a Kubernetes cluster under the covers, which is interesting. But it also means that we can now start to understand a little bit more about the architecture and start to poke explicitly again for Kubernetes bugs because we know that that's the underlying orchestrator under the covers. There's other things like we can do and poke around, look at the kernel version. We can look and see what other things are installed. It's been running for when I connected and launched it for the first time, it was running for 46 minutes. Now that could indicate that it's a shared VM running, sitting there, and there's other people connected to it, which would be surprising in some ways because Azure is not sure of VMs. But it's also strange that I would have so many VMs just sitting there idle, waiting for people. So we can start to poke around and see what the capabilities would be there, and again, trying to find additional attack vectors off the back of this. And because if this was a shared VM, we can see that there's a disk and we can access certain files and certain capabilities. If it is a shared VM, we can just write all of the data to it. We can just write dummy 0 data, fill up the disk, and as such, that would kill our session, but if it was a shared VM, it would potentially kill other sessions on the back of it. And with Docker, the way that the mounting works is that every container will have the XCD host file mounted in. And if you're running as root, you can always write to XCD hosts. And this will then write to the parent disk, which has got 0 file storage limits attached to it. So now you can fill up XCD hosts with random garbage data, and that will then be stored on the host, which doesn't have any code to attach to it. And as such, that will fill up the disk and take down the host, which if you're just trying to do resource consumption is a very quick and easy way to achieve it. In other container orchestrations, they've resolved this issue. So Podman, which is a container orchestrator, container runtime from Red Hat, or sponsored by Red Hat. And what you'll see is they've taken this approach and they've mitigated it. So we still have the C groups being defined above. So we can see it's libpod, which is the process, which is the library under the covers of Podman. But if we list all of the file systems, then we can see that the host file now has a limit of 100 meg, more than enough to list every single host, which I would imagine we'll ever need to do, but not enough that we could accidentally fill the disk, the host level disk itself. And again, one level of protection against resource consumption. The other resource consumption, which I'm always a great fan of, is this beautiful bit of bash scripting. So to break it down, we're defining a new bash function called colon. The body of that function is to call a function called colon and to pipe the output of that to another function called colon and to then release control. And then after that function's been defined, call the function called colon. And this creates a beautiful fork of all of these processes where 1 becomes 3 and 3 becomes 10 and etc. And you can tell this is happening on a system because the system load will go to 4,000. Processes will spike and start to zombie out as it runs out of resources. And then this is the last you'll ever see of the host in question. And you'll have to do a hard reboot because all of the processes have been taken over, all of the resources have been consumed, and there's nothing which you'll ever be able to do apart from do a hard reboot by pushing a button on a server or logging into the cloud platform and doing a hard reset. This is not fun, it's not entertaining, it's just really annoying. So with Docker, they now have introduced a limit of how many processes a container can launch. So when you can start a container, you can set a reasonably sensible number, for example, 1,000 processes, which can be launched. This means that your application can continue running, continue doing everything it needs to do up until it hits this PID limit. And as soon as it hits this PID limit, it won't be able to create new processes. So if someone does run a fork bomb, it will only be able to run, in this case, 500 forks of this process until it consumes all of the resources. but it doesn't consume all of the resources on the underlying host. And again, if someone was just being malicious, then we're having these layers of defense out of the box. And this is just a sensible default that should be applied to everything, in my opinion. And we can now define this if you're within an orchestrator like Kubernetes, it has the API hooks to set that in place too. So these are some of the kind of things which we see which people are attacking the kernel, or the fact that it's a shared kernel and trying to look for additional vulnerabilities, or the fact that it's a shared underlying host and they're trying just to exploit and consume all the resources. But what about the attack at a network level? So a common attack, which you'll see all the time, is DDoS. It's always a favorite from the last 10 years, and it's just trying to take down an external system because they're exhausting all of the network traffic, so they can't handle everything, can't handle legitimate traffic. So this is the first sign you'll see of a DDoS attack happening is because your hosting provider will become very unhappy with you. This happened from a couple of years ago now, and I got an email from DigitalOcean, as it was at the time, saying we've had suspicious activity and we've cut you off the network. And this is suspicious activity was this huge network spike as someone found an open container to the internet and was then using that to launch DDoS attacks, which was great. Other attacks which you'll see commonly, like Nmap being run, where people are doing port scans to try and look for potentially vulnerable systems, and obviously to do that on a system which isn't their own, so they can't be traced or blocked as easy. It's great to do it from a third party. And these are difficult to attack and difficult to block because unless you're doing like completely blocking via the egress, which I mentioned, it's very difficult to block based on a rate limit or based on seeing too many active connections happening. And so there's not really a great way to solve that. When it comes to internal attacks, we also have a similar kind of capabilities or kind of like similar concerns. So in terms of when we're doing things like running on top of Kubernetes, we can start to poke around the file system and see if any of the defaults, like API servers are available, if any of the accounts or tokens are in place, and then seeing if we can utilize these. Now, in the latest versions, these are off by default, but older previous versions still had these enabled. And so if you have access to the token, then you could potentially use that to call the API server. And if you can use that to call the API server, you can start to understand poke in interesting ways. Other ways of being able to jump from the container which you're currently in to other things running on your network. And we can limit that through the network policy and network policy capabilities. So we can start to draw these firewalls or these boundaries of particular types of our system and what they can or can't talk to other parts. So for example, our web front end can talk to certain APIs, but it should never be able to talk directly to the database. That should always go through an API. And we can start to build up these barriers and restrictions so that if our web front end does ever get exploited for a particular reason, then we can make sure that it's never going to access the database directly. And likewise, similar to what we can do with Istio, we can have a network policy which would just block all of the egress, all of the outbound traffic from that. If we know and can guarantee that all of our traffic is always internally, we can just apply a network policy to ensure that restriction. And that kind of gets us to this kind of system which I talked about, where we can keep our containers more secure from talking to external parties, like what we could do with Istio, but we can just do it at the Kubernetes level too. So with all of this happening and all of these things under the covers, we can defend and we can mitigate and we can block attacks, but we need visibility to make sure that we're actually seeing these things happening and to make sure that we have the right defenses in place and we're not missing anything within our defenses. So there are a couple of ways. If we're using IP tables, we can log any single packet which we're dropping, and we can prefix this with a particular kind of string, so we can make it easier to search for. And all of these IP table logs will be logged to system var log slug. And as long as that's been aggregated to like Datadog or another logging service, then we'll be able to monitor and alert for those capabilities. But there are more advanced projects now, which give us a lot greater insight and a lot more control than what we'd have above and beyond networking and above and beyond networking capabilities. So one is a tool from Falco called Falco from Sysdig, which is now part of the CNCF project. And this allows us to define alerts based on behavior and based on what's happening within our system. And if an alert happens or gets triggered, it can push into a Slack channel or go into other notifications that we need to based on the severity of the event. So for example, this is what Falco rule looks like. This is detecting commonly used minor ports. So if a new port connection gets created and that the source of that port is in this array, then it will trigger a warning that is happening, and then that warning can be sent to Slack, for example. So now we can start having visibility into something malicious or something unexpected is happening in our system, and then we can jump in and we can actually be proactive into finding exploited applications and closing them than what we would have before. And so the Falco is great, and there's lots of rules and lots of controls. For example, it writes into certain directories, writes into certain files, opening ports, for example, that we can create these rule boundaries around. But it's also important to make sure that we have a good security pipeline in place. So we want to make sure that the images which we're running in the first place are the images which are trusted, they are what we expect, and they are adhering to the certain network certain restrictions that we should adhere to. And so we don't get this memtest kind of exploit with Bitcoin happening under the covers. So there's certain platforms which will help us with this. Twistlock, Aqua Security, cloud hosting providers now have their own solutions. And these will run monitoring and alerting against a container, and also things like compliance checks and behavior checks against what's happening and how that container is being utilized to make sure that we're not running anything which has got known security issues. And if it's behaving unexpectedly, that's being alerted and the team are aware of it. And we can make sure that if we're running something in our system, this is the example from Aqua, then and a security vulnerability gets released against it, then that's going to be alerted and that's going to be notified. And then the system can take action, for example, blocking anything with a critical vulnerability being pushed into production, or making sure that if it does happen, certain teams are alerted so they can defend against it. And so this is an overview of what I wanted to share, some of the lessons which we've learned, some of the capabilities that we have in place, and some of the ideas which you can think about when you're planning how secure your systems are and what needs to be in place. But it always begs the question, like, are containers secure? Well, containers are secure as long as you have the right level of security in place. If you can run Docker and run everything as privileged containers, no, they are not going to protect you. They are not going to provide any security boundaries. If you're following good book guidelines, you're locking things down, you have a good security pipeline, you're going to be much better defended than what you would be otherwise. But there's always things that you need to be on top of and things that you need to be aware of. And it's not just containers, like VMs also have their own security capabilities. This is one from KVM, which allowed memory access because it attacked the floppy disk driver in an interesting way. And so then via the floppy disk driver, it could access the memory and access the memory of the host. So there's always vulnerabilities, there's always problems within systems. We need to acknowledge that. We need to take that into consideration, make sure that we're applying everything which we need to be as secure as possible. And to do that, there are a couple of quick wins to keep us as secure as we can be. So firstly, don't allow containers to run as root. It's a very easy, quick win. Most applications don't require root privileges, or if they do, they're easily changed and updated to mitigate that. Again, if you're running a container in production, there shouldn't be a reason to install additional packages, change certain files. It should always be locked down. So needing root shouldn't be a requirement. If you do need root, then use user namespaces so that the root level permissions inside of a container isn't the same root level permissions as what's running on the host itself. If you don't need to be making changes, you can actually enforce that. You can make the container file system read-only and block any changes happening. So for example, if it does get exploited, people won't be able to change the JavaScript or the CSS or the HTML to do a homepage attack takeover because the file system's read-only, then all changes will be blocked regardless of if they get into the system or not. Again, if we're blocking file systems, can we go a step further and block egress outbound traffic? Like, do we need to have access to the entire internet running from in production, or do we just need access to one or two APIs to make our system be able to work and communicate with what it needs to? And this is where things like Istio, service meshes, network policies, all of these APIs are there to support this capability and having much more fine-grained control over which parts of our system can talk to each other and being able to easily block that if we don't need to. And above all of this, we need visibility. We need to know what vulnerabilities exist within our system. We need to make sure that our containers have come from a secure pipeline, that they have all of these things in place. And we need to make sure that if attackers do get in, we're being alerted about it. It's being monitored, it's going to somewhere which is visible and it's actionable, not just a log file on a server which no one pays attention to until 6 months after it's happened. And this is where tooling like Falco is really fantastic, and it can give you that control and visibility for strange things happening in production. And so that's everything I wanted to share today. If you have any questions, feel free to ping me on the NDC Portal Slack channel, or reach me on Twitter, Ben_Hall, or email me directly, ben@katacoda.com. And if you find anything interesting on Katacoda, anything which we've missed, anything which you think is great and you want more of, then do let us know. We're always open to feedback, and we want to hear what you think and how the platform can help you learn and keep your system secure. So with that, thank you very much.